So good morning, everyone. It is my great pleasure to welcome Richard Davis from BIPM, presenting on how the international prototype kilogram, the Le Grand K, or the Big K as affectionately known, became the last artifact. This is probably the 8th or so Kelly presentation in our seminar series. We had a good pleasure to have speakers from all around the world sharing their knowledge and stories about analytical chemistry, statistics, and today we have Richard Davis from BIPM.
So I will talk about how the people like to call it the Grand K, Big K. I'll say how it became the last artifact. I'll also say how it became Le Grand K, so you know why it has that name. And the story basically starts because you can't talk about the last artifact without talking about the first one. So the first one was envisioned by a royal decree in 1791, where it's the age of Enlightenment. They got together, the French scientists got together and decided they needed a new system of units based on decimals, and also they wanted it to based on measurement that was natural and invariable. So that was forward thinking. And it was given royal approval in 1791. There was still a king. France was briefly a constitutional monarchy before the king was guillotined, and he approved this proclamation. So the meter, as you probably know, is based on the quadrant of the Earth's polar circumference, which would be 10,000 kilometers. So there's a picture of the meter, 10,000 kilometers from the North Pole to the equator, conveniently passing through Paris here. And they only measured the part in France, so they extrapolated the meter based on that little bit. And they knew the Earth was, they already knew the Earth was slightly oblate, a little squashed at the top and bottom. And they knew this because earlier in the century, expeditions from France had gone to the north near the Arctic Circle and made some measurements, and also down to what is now Ecuador on the equator, and made some measurements there, and they'd made measurements in Paris. They knew the Earth was not a sphere, and they of course took that into account. Of course, when you make a new unit, you have to figure out what it is compared to the old unit, which was the toise. So that was something that needed to be done. And then they worried about, well, we're going to make a sort of materialized version of this, make a meter bar. And then if the artifact standard is destroyed somehow, this new standard has to be reconstructed. And they were going to do that based on the length of a pendulum that beats the second. So that would be in Paris. So as long as the pendulum is always in the same place, it should always, you should always be able to find the meter from its length. And then once you have the meter, you sort of get the kilogram for free, because the kilogram is just based on water. Water's everywhere. So a cubic meter of water weighs a ton in this system. And so a cubic decimeter weighs a kilogram. And there was a report on the work, but not a really full report. So there was a report given in 1799, but not by, about the work of Monsieur Lefebvre-Ginot, but it was what his report wasn't written by Monsieur Lefebvre-Ginot. It was written by a Monsieur Tralles. So we don't really know what Lefebvre-Ginot did exactly. And so that's one of the mysteries. But it produced a kilogram. And so they did say, though, that the kilogram must equal the weight of the cubic density of water at its maximum density. So we know that maximum density is about 4 degrees Celsius, almost exactly. But you don't need a thermometer to find the maximum density. You just need to start measuring densities and find the maximum. And you know that's. And there's a school book version of this definition where you start with 2 identical empty recipients. In one of them, you put a liter of water, and the other one, you put a kilogram, a metal kilogram. And except for air buoyancy corrections, they will balance when they're equal. So, and they knew all about air buoyancy corrections. They knew all about everything. So it was pretty good. But preliminary measurements were carried out originally by Antoine Lavoisier and Hauy, who was sort of one of the founders of crystallography. And it was preliminary because provisional value of the meter was used. They didn't really have the final value. And you need the meter to get the kilogram, and you need distilled water, but they didn't have distilled water in enough quantity. So they got filtered water from the Seine, which was nearby the laboratory, and they would need to compare the density of that to the distilled water. They nevertheless produced an interim report in 1793. Lavoisier was guillotined in 1794 for having run afoul of the what's now known as the Terror. And how he returned to his work on mineralogy, and a new team took over. But they did write this report, which you can find on the internet if you look hard enough. And it says, just to start with, Messieurs Lavoisier and Hauy were charged with determining the unit of weight. They called it weight, but they knew it was mass, coming from, and they needed to get a preliminary result essentially for the exchequer so that they could start making money at the mint. So, and that's the introduction, and then they tells how it was done. It's quite interesting. So just to sum up, Antoine Lavoisier, because he's so important in chemistry, he showed that mass is conserved in chemical reactions, which kind of destroyed the phlogiston theory, and he was keenly interested in analytical balances and mass metrology, and he wrote his famous elementary treatise on chemistry. He was helped by his wife, Marianne Paulze, who lately has come into her own because women were largely invisible in the past, and yet she contributed quite a bit. And so, and there's this painting in the Metropolitan Museum in New York City done by Jacques-Louis David and the title of the painting is Antoine Laurent Lavoisier and his wife. If you look at it, when I look at it, it's a painting of Marianne Paulze and her husband, because she's the one who's all lit up and everything, and he's kind of a cartoonish character looking at her, and she's looking out. Anyway, so Marianne Paulze lived a long time after Lavoisier was guillotined, and she had the misfortune that her husband and her father were guillotined on the same day. So now the next team was Lefebvre-Ginot, Fabroni, Fortin, Giannetti. they started to make a new kilogram. Lefebvre-Ginot was certainly, everybody said, was talented in the laboratory, but he never wrote a report. We don't quite know what he did. Trollis's report is helpful, but it doesn't get as far as the archives kilogram, which was the kilogram. And anyway, they these teams produced, on the left, you see the archives kilogram in its little box, and then there's the meter, and that's a meter that is 1 meter from the ends. It's an end meter, end to end. And the meter that was made later was a line meter, which was 1 meter between 2 scratches on the bar. But anyway, so on the top of, there's a blow up. Terry Quinn, who some of you know, took the photograph of the top of that box once it was closed, and it has this little thing on it, and it says it was certain dates of when it was made. And at the bottom, and these are the revolutionary calendar years, and which were used at that time. And at the very bottom, you can see it says 410F, 410 Facit. So it was 410 who was made the balances, who made the kilogram, and he put his name on it. So then we moved to England. What was going on across the channel? So this is only 25 years later, and England passed a parliamentary act about weights and measures, and it included what to do if the troy pound, which was the standard of mass, the weight, was destroyed. That's interesting, because what they said to do is the same thing that the French said to do, essentially. It is expedient that the troy pound, if lost, destroyed, defaced, or otherwise injured, should be restored to the same weight by reference to some invariable natural standard. Exactly the same words, invariable natural standard. So this is what they all wanted. And the standard shall be restored by making a new standard troy pound bearing the same proportion to the weight of a cubic inch of distilled water, as the said standard pound hereby established bears to such cubic inch of water. So this is important because, as we all know, stuff happens. And what happened was in 1834, the Houses of Parliament burned down. And so what first thing you do is establish a committee, and the committee looked in the ruins and reported that all the standards of measure and weight were either totally destroyed or injured to such an extent as to render them quite useless. The imperial standard troy pound was never recovered from the ruins. So that's about as bad as it gets, unless somebody's killed, but nobody was killed. So that was bad enough. So, so then they set about to replace the standards as the law prescribed. And they learned a lesson that you couldn't do it that way. And they decided, well, you know, if you want to make a new kilogram, the easiest thing is to just find a bunch of kilograms that didn't get destroyed and they're high quality, and bring them together and take a kind of average, and do the same thing for the yard. Well, in this case, sorry, it was the pound in the yard. And they found that that was the way to do it. So that was a good lesson. And it showed that there were the same, more or less, prescription made in the French system probably wouldn't work either. So then this guy Miller went ahead and made the pounds for the English, and he decided to take the opportunity to compare the new imperial pound with the kilogram of the archives. So we know a lot about the kilogram of the archives because he came in the mid-century, he came over to Paris and to the archives. The archives set him up in a little laboratory. He was able to use the kilogram of the archives, and he made a standard weight. And you notice that W.H. Miller, William Howells Miller, was a professor of mineralogy. And if you've ever taken a crystallography course or something, you probably had to set up crystals based on their Miller indices. And this is the Miller who made Miller indices. He was later a member of the International Meter Commission that recommended the establishment of the BIPM in 1875. So he's kind of an interesting figure. And we learned a few things from his report that weren't published anywhere else. We find that Giannetti, he was not a scientist. He was considered an artist. He was a goldsmith, but he developed a process for refining platinum ore. And it was a process involving arsenic, which surprisingly didn't kill him. And there are details you can find in a book by MacDonald and Hunt. I just picked one sentence out. Maybe it's too small to read, but it says, having obtained a non-magnetic alloy, he melted it with a little more arsenic and potash. So, I mean, it goes on and on. It was very difficult. And sometimes he had to do this 3-4 times. He also found that they had forgotten, or more likely just hadn't written a report about it. No one really had a good value for the density or the volume of the archives kilogram. It was 1 kilogram. So if you know its density, you know its volume. And but they only had a very rough approximation. And he wanted to measure its volume, first by hydrostatic weighing, but they said, no, you can't put it in water because it's got arsenic and who knows what else is on there. So they agreed to let him use a pycnometer, air pycnometer, and he got a volume. And he found he found the volume or a density 2549. And we know that platinum, pure platinum, would have a density about 21,460. So it was, that kilogram had 4% of bubbles or air or stuff. Almost anything is lower density than platinum. So it wasn't pure. There are a few acronyms for people watching on YouTube. I think everyone in NRC knows this stuff. So, and anyone who's interested can go to the BIPM website and look up worldwide metrology. But there's something called the General Conference on Weights and Measures. It's an intergovernmental body that meets approximately every 4 years. It approved the revised SI last November. That's the body that gave it official approval. And then you can read a lot more about it. And the CIPM is the International Committee for Weights and Measures, 18 members, different nationalities. There's a Canadian member, Alan Steele, who is at NRC. So it meets every year. So neither of those groups have a permanent seat, but the BIPM is permanent. And there's a picture of the entrance to it at the bottom. It's in Sèvres, a suburb of Paris, and you're looking in at the Pavillon de Breteuil, so-called. That's the oldest building on the site. There are other buildings that are much newer. Moving right along. So the BIPM was tasked with making international prototypes for the kilogram and the meter. And to be ready, they were ready by 1889. And they also had to make national copies to be distributed to the national laboratories of different countries. So, but before all that, there was an International Meter Commission regarding the creation of K, Grand K. And it's, they said its material should be platinum alloyed with 10% iridium to make it harder. They knew how to make it with higher purity, and they said, yes, it must be made with higher purity than the old stuff. And both alloys, the same alloy should be used to make both the meter and the kilogram. And then the big question was, should they go back to the density of water? And they said, no, just go back to the kilogram of the archives. So that, because what if the archives kilogram is pretty far from the density of water? No one's really measured density of water since then. And so they didn't want to cause a big discontinuity in people's measurements, or even a small discontinuity. And so they had to go back to the archives kilogram, which they did. Okay, and then there's another chemist I want to point out, Jean-Servais Stas, Belgian, and he was a member of the CIPM from its inception until his death in 1890. As a CIPM member, he actually worked as a CIPM member in measuring the purity of the platinum alloys. And so he found, in fact, that there was one huge batch of alloy, the 1874 alloy, that didn't meet the purity requirements, which were kind of arbitrary. But he said, even if they're arbitrary, I'll just let you know you didn't meet it. So there's a huge brouhaha about all that, and so he left and made his mark. Now the symbols. So here you can find in the Travaux et Mémoires du BIPM, it's just a bunch of papers, scientific papers, generally. And you can find them not on the BIPM website, but on the Library of France website, the Bibliothèque Nationale de France. So at the top is what they said in French, and at the bottom is kind of my translation, and it says, first it's a quote from a previous report: kilogram K3, whose mass was found to be identical to the archives kilogram by the mixed commission, was chosen to be the international prototype of the kilogram. So they knew that. So then the author of this paper said the kilogram K3, thereby selected as the international prototype, was henceforth represented by the symbol, and this is a Gothic font K. It has no identifying mark. So that's how you can tell it's the international prototype, because all the others have a number on them. The international prototype doesn't have a number. So because they found its mass was identical to that of the archives kilogram, but they hadn't engraved a number on it. So they said, okay, we're not going to engrave a number on it and change its mass. So it has no mark. And but it was referred to as with this Gothic K. If you look closely, I couldn't find the same font as they used back in the 1880s, 1890. 1893, but it's a Gothic font. And the meter, we forget about the meter, but the meter was also designated with an M, Gothic M. Okay, so an artifact definition, just to remind you, what it means is if I have some object X, let's say it's a powder or something, and I want to know what its mass is, I find the ratio of the mass of this powder to the mass of the international prototype, and that's a number, and then I say that number times a kilogram is the mass in kilograms. And not a practical system, so you have to have a way of disseminating the kilogram, and it's done, a very kind of simplistic way of doing it through this equation. So you have the international prototype here, the secondary standards at the BIPM here, and then you go to the national laboratories and their primary standards, and then on and on and on, multiples, submultiples maybe, and then finally get to what you want. And the system works because the same thing appears, the same mass appears in the numerator and the denominator, cancels out if the masses remain stable. It's always a big question. And you end with what you want, which is the mass of your unknown to the mass of the kilogram. And there are buoyancy corrections and everything I've left out. But so it's not a very convenient system, but it has worked. And you also need a system to measure the mass of maybe atoms or something like that. You won't get as accurate a result, but you need to be able to do it. Okay. Now, 50th anniversary of the BIPM. The president, the director of the BIPM, Charles-Édouard Guillaume, who also won a Nobel Prize in 1920 for discovering INVAR. He wrote a book about the BIPM and the kilogram and the meter and everything. And he said, one of the things he said was, it thus seems that the unit of mass is assured to be about 1 × 10 and 1 part in 10 to the 8th for more than 10,000 years. And this period has scarcely begun. So how did he get that? He got it by extrapolation, obviously, and by an assumption that if you left the mass in the safe and didn't really use it very often, the mass would never change. That's a pretty big assumption, and it's a pretty big extrapolation. But anyway, he said, no doubt well before it ends, work carried out by metrologists in future centuries will have led to even more flawless solutions. So, so that was where I guess things stood in 1927. But the question you might ask was, how stable was the archives kilogram over 50 years? And you could find out because you could borrow the archives kilogram back again. It hadn't been used, maybe just a little bit by people like Miller, but not much. And they found out that over 50 years, in 1939, when it was measured, it was 400 parts per billion lighter. Because in the 1880s, it was exactly 1 kilogram, you know. So now it was lighter. And they were moved to make this measurement because people had noticed that other platinum standards that were made early in the 19th century were also getting lighter, just sitting in the box. And they didn't know why, and we still really don't know why, but it seems to have been true. So if you do the extrapolation, you would say that between 1799 and 1883, the archives kilogram had lost 600 micrograms, which for the balances of the day was still not an enormous amount. Hard to see, but you could. I think by 1880s, you certainly could have seen it. And this is all assuming that the international prototype had a constant mass. But how stable is the mass of Le Grand Cas? So, well, we'll get to that in a second. The metric system became the international system of units in 1960 during the 11th General Conference. And André Dangean, the CIPM president and director of the Paris Observatory, made the following statement at that time: of the 3 fundamental quantities of mechanics, and the fundamental quantities of mechanics for him were mass, length, and time, only mass will continue to be defined by an artifact standard. He said the platinum iridium kilogram at the Pavillon de Breteuil, which is the BIPM essentially. But we must recognize that its invariability depends on a small miracle. In practice, it is rarely used for fear of changing it. And that is entirely true. And he said that is a weakness of the SI for which metrologists must sooner or later provide a remedy. And that was 1960. The remedy was provided in last year, so on May 20th. So here we go. So then what happened? So I was just a kid in 1960, but I was at the BIPM in 2003 when this news item hit the papers. New York Times article, scientists struggling to make the kilogram right again. The kilogram is getting lighter, scientists say, sowing potential confusion over a range of scientific endeavor. So who said this? Scientists said it. Okay. These are actual quotes, but wait. Here's the Telegraph of London from 2013. It's official. The kilogram is getting heavier. The kilogram has been getting heavier, meaning we are all getting slightly lighter, experts say. Who said it? Experts say it this time. Last time it was scientists. And those are other actual quotes. So you know you have to do something even if you don't have to do anything. So when these kinds of articles start coming out. So lighter, heavier, compared to what? They never say. And so you have to compare the mass of the international prototype to a quantity that is, well, in 1791 they would have said natural and invariable, and 2011 we said a fundamental constant of nature. And then it's pretty hard to do, and it really is hard to do. So what atomic physical constants were available to redefine the kilogram? Constants I've shown in red were seriously considered. So you could have had the atomic mass of carbon-12, make chemists happy. Subatomic mass of the electron, because it can be measured quite well. And physical constants, Planck constant. Well, the Planck constant has the kilogram in it. It's kilogram meters squared per second. So if we know the meter and the second, their definitions didn't change last year, so that they're the same as they had been for decades. So you can get the kilogram from the Planck constant, and the Planck constant is quite useful. The atomic mass constant, which is a sneaky way of getting the carbon-12 mass back in there, because it's just the mass of carbon-12 divided by 12. And then the Avogadro constant, and its unit is the inverse mole. So where's the kilogram? I mean, how do you get the kilogram out of that? So you get that because of this equation. The molar mass constant is 1 gram per mole, and it's been fixed. So and that was fixed to be exact. So under those circumstances, if you measure the Planck constant, then you do get the atomic mass constant, and you can redefine the kilogram that way. And in fact, this is an equation that Zoltan and Uris and others have seen. So this is an identity, Planck constant divided by the what happened? Sorry about that. And it's exactly equal to the Avogadro constant times the Planck constant divided by the molar mass constant. And that is equal to something that has a very well-known value, but it's not 0. And also it's something that cannot be defined. So you can't fix the value of this Q, even though we know what it is, to pretty high accuracy. You can't fix its value. So your choices here are, you can fix the Planck constant, but then you can't fix the atomic mass constant. Or on the other equation, you can fix the Planck constant. You can fix any two of three, but not all three. So the choice that was made is the molar mass constant had been fixed in the old system, and in the new system, the Avogadro constant and the Planck constant are fixed, but the molar mass constant is got this slight uncertainty coming from this Q on the right side of the equation. Won't go into it any more than that. And they picked the Planck constant for the kilogram redefinition, but the Avogadro constant was picked just to have a constant and define the mole, because its unit is inverse mole. So here's a 74 paper. A lot of you know anyway, especially at NRC, because you have the best one, the Kibble balance to measure measured the best value of the Planck constant. But Kibble published his original proposal for that balance in 1975. In 1974, there was a paper that came out about the Avogadro constant. And the paper concluded, it measured things to about a part per million or something like that. But they said, you could do better. That wasn't the end of the road. So the paper concluded it would be thus appear that a value of Na is obtainable with an uncertainty of an order of 10 parts per billion. Should this be achieved, one might wish to assert that the artifact kilogram is redundant and that masses can be obtained via an algorithm of realization from the atomic mass unit. So this has been going on for a long time. 1974, 1975, it's taken a long time to do it. These are difficult measurements. Getting that last factor of 10 is really tough. Here's my colleague Estefania de Miranda has made this thing, and these are uncertainties. These are relative uncertainties of the Planck constant. It's not values, it's just their uncertainties. And the uncertainties follow something like a Moore's law. If you start here with Planck himself, and then you work down, and as time goes down, technology improves and the uncertainties get lower and lower. And you can see that you're going to hit the target right around here, which happened. And it's very strange because new technologies came along. They didn't have to. I mean, you can't just sit back and wait 100 years and everything's going to be better. You have to keep working. But it seems, and the Planck constant is not the only one. You can see this in many other constants. They do follow this sort of approximate logarithmic law for uncertainties of the constant. Now, if I showed the values of that, they'd be bouncing all over the place. But if you look at the uncertainties on a log plot, you see something that looks kind of interesting. And then Burge, who did the first adjustment of fundamental constants, everybody's value, he did two. He did this one and he did that one. And during that time, by 1941, he concluded that it's only when thoroughly consistent results have been obtained from radically different methods that any real reliance can be placed on final weighted average value. So yeah, he found that didn't matter how talented you were and how much money you had. If you were the only one to measure something, you probably didn't have it exactly right. So that's all interesting. So I think, how are we doing on time? Getting there. So I'm wrap this up. Just go through conservation of mass. Summary, I'll start here with Newton, 1687. The conservation of mass has been called by a Nobel laureate, Frank Wilczek, as the zeroth law of mechanics. That is, it's so obvious that you don't even bother to mention it, that in mechanics, mass is conserved. But, if it's so obvious and you don't mention it, you're kind of surprised when you find out it's not true. So Then we hit Lavoisier in 1773. And I will just mention here, and at the bottom of the slide, there's a zero theorem for the history of science, not, and that theorem says the person who gets the credit for something is rarely the person who actually did it. And in Lavoisier, I think a good case can be made for conservation of mass, but Lomonosov published a paper that said much the same thing about 20 years earlier. And there are plenty of other examples. Loschmidt made the first real measurement of Avogadro's constant. And there's a long list of these things. Planck himself had, in his paper about black body radiation, he had two constants that he invented for this to solve this problem. And one is now known as the Planck constant, and the second is now known as the Boltzmann constant. So, and Planck used to call that my second constant. But anyway, Einstein, 1905, special theory of relativity, which implies that mass is not conserved in chemical reactions, but these changes are too small to observe, and therefore they couldn't test special relativity with chemistry. And you know, why you might see something is because there are chemical bond energies that when you have covalent bonding or you make chemical reactions, the bonding energies change, and a mass balance, an analytical balance can't tell the difference between rest mass of something and mass energy divided by c squared, as long as it's in a rest frame. So today, chemical bond energies can be weighed, special relativity rules. So measuring relative atomic masses of nuclides requires small special relativity corrections to achieve maximum accuracy. And you can see this in it's an organization called CODATA that puts out least squares adjustments of the fundamental constants, and you can see how they deal with this, and they do deal with it. And we, therefore, even though we haven't seen it, we can confidently predict that a 1 kilogram monocrystal of silicon-28 has a mass that is smaller by 2 parts in 10 to the 10th than the mass of an identical number of free atoms of silicon-28. So where's the missing mass? It's accounted for by the energy of covalent bonding. This mass defect remains negligible for metrology and chemistry, which is good. So chemists can still use mass balance. And this is an interesting paper by Jackson where he gets all these zero theorem things throughout history, and it's in other subjects too. People are given credit for in mathematics for theorems that other people were first to find. So that's another interesting thing you might want to look at someday. And so just summed everything up on the last slide that we've been talking about. You know, I didn't talk about actually how you measure the silicon crystals, use silicon crystals to get the Planck constant or the Watt balance, because that's another talk. But let's just say you can do it, and it has been done. And then here, you've seen most of it. Here's a picture of Planck and Einstein at a conference. And Planck's equation, energy equation, Einstein's energy equation. You put them together and you find that you can get mass these are two fixed constants. Mass is a function of frequency. So this is kind of a frequency transducer for mass. And that's basically what a Kibble balance is if you look in great detail at how it actually gets the final result. The Planck constants is really important in electricity. These are two living Nobel laureates with constants named after them. They're important in electrical metrology. Brian Josephson is Josephson constant. E is the elementary charge of matter. And this is Klaus von Klitzing. This is the von Klitzing constant of resistance. H over E squared turns out to be about 25 kilo ohms. So I think that is my talk. And if there are questions, I would try to answer them.
Thank you very much, Richard. Very, very interesting, entertaining talk. I would like to ask my colleagues if there are any questions. Maybe I will start off with a question. So you talked about the long-term stability of the IPK, that it's lost 400 microgram, gained 400 microgram, or
no, that wasn't the IPK. That was the archives kilogram.
Oh, I apologize. The archives
assuming that the IPK was stable, which I think it was.
Oh, so that was against the IPK measure. Okay.
So then the question becomes, what about the IPK?
Of course.
I have a slide about that, but no. It's hard to say. It's very hard to say. Those numbers are limited, and it could be gaining mass, it could be losing mass. I'd be happy to know what the answer is. But now that we have a really good definition of the kilogram based on fundamental constants, it will still take years to find out, if we even want to find out about the, because whatever the change is, it's relatively small. And so if you have a measurement that's good to 20 micrograms, and you're looking for, and you want to see a change in 20 micrograms, but you're looking for 1 microgram a year, which is what people are looking at, then it would take 20 years, but it'd take more than 20 years to be sure. You'd want to get 2 sigma or something, so you need 40 years. So I think we just changed. They used to say, well, we'll change the difference when we'll see the instability, but we know it's unstable because it's an artifact standard. So let's just get rid of it. Use something that is stable. Even if it's 20 micrograms uncertainty, it's always going to be within that 20 micrograms. And so that you win, it's a win. So that's what was done. And maybe technology will improve, but it's just a question. It's kind of a question you would answer for a bar quiz. Is the kilogram changing? You don't care anymore because it's been redefined out of existence. That kilogram, the unit remains. Yeah.
Thank you. You served for 20 years as the head of the mass department of
almost. My predecessor, there was a 3-year overlap with my predecessor. They used to be able to do that in those days. You could sort of learn from the person who actually knew how to do it, and for a few years, and then gradually take over. So yeah, so 17 years, let's say.
So have you seen the IPK? Have you touched the IPK?
Yes.
Have you touched the IPK?
That is a good question. The person who touches it is the one who cleans it. I mean, otherwise you don't really touch it. I picked it up, I picked it up, and I've had it in tongs and everything, but I've never, when you have to clean it, you would be, the only thing between your finger and the IPK is a piece of chamois leather or something. So I've never been that close, but I've picked it up with tongs, and I've moved it from its old safe to the new safe, and that kind of stuff. I mean, so the question people would say was, when you're removing it, are you afraid of dropping it? And I would say, I'm afraid of a lot of things, but I wasn't afraid of that. So, otherwise you couldn't do it. If you're afraid of dropping it, you will drop it. I believe. So, But you get used to it. You get used to everything. You know, you're at an RC and the people are using, you have platinum kilograms. You have ones that you don't want to drop and you don't want to damage. And people are careful with them. So you just learn to do it.
Thank you very much, Richard. We are coming up to noon in Ottawa time. I would like to thank you again for coming to Ottawa, even if virtually this time.
My pleasure. Well, it's getting to be a time for an aperitif here, so
enjoy your evening.
Glass of wine, yeah, okay.
And I would like to thank all of you who joined, and see you in our next seminar.